And liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
In 1986, the Space Shuttle Challenger exploded seconds after launch.
Obviously a major malfunction.
7 astronauts died.
That the vehicle has exploded.
Negative contact.
And the disaster marked a turning point in America's space program.
Can we get any reports from recovery forces? Stand by.
Space travel would never be the same again. And it was all because of the weather. Around the world and throughout time, weather has played a part in the fortunes of mankind. Violent events in our planet's atmosphere have transformed history. These are the stories of weather that changed the world. For the last 50 years, NASA has pushed the boundaries of space exploration. They were the first to land a man on the moon.
They've got the flag up now.
They've sent probes to far-flung corners of our solar system and put a space station into orbit.
5, 4, 3, 2, 1.
And in 1972, NASA started the Space Shuttle program. 135 flights over 30 years have done more to help further our understanding of the universe than any other space program. But in that time, NASA endured a shocking tragedy. January 28, 1986. Challenger explodes 73 seconds after launch. Burning debris rains 8 miles down from the sky. The entire crew perishes, amongst them Krista McAuliffe, who was set to become the first teacher in space.
And here comes the flight crew now.
The dream of safe, routine space travel looks further away than ever. Hours after the explosion, an investigation to determine the cause of the tragedy is underway.
The shuttle is the most complex system that has ever been built. It's got thousands of connectors and components in it that all have to work properly in order to have a safe and successful mission.
When disaster teams recover the wreckage, analysis shows that out of 2 million components in the shuttle, one small part failed. It's a flaw in the shuttle's complex engineering, but it failed because of the weather.
Weather was one of the most common causes of delays of landings and launches of the shuttle. Despite its size and its power, the shuttle was actually very sensitive to the weather, and not just obvious things like lightning. The shuttle absolutely could not land or launch in rain. Low cloud ceilings and even crosswinds that were too strong could all delay shuttle launch or landing.
January 27th, 1986, Kennedy Space Center, Florida. Challenger's mission is 5 days behind schedule. Conditions for launch are perfect, but there's a technical hitch.
Yeah, we got a problem on removing one of the screws on the milk stool. It appears it might have to be drilled out.
And by the time engineers have fixed the problem, crosswinds at the emergency landing strip are too high. NASA delays the launch until the following day. But by then, a cold front from Canada is expected to reach Florida.
The expectation was that temperatures that morning would bottom out in the low to mid-20s, in record-breaking territory.
Despite a forecast for freezing conditions, NASA continues with launch preparations. But 2,000 miles away in Utah, engineers with one of NASA's suppliers are worried the weather could cause problems. Aerospace contractor Morton Thiokol designs and builds 2 of the shuttle's key components, the solid rocket boosters. At takeoff, the shuttle sits on top of its huge external fuel tank. Either side are the 2 powerful rocket boosters. They burn for the first 2 minutes of every flight and give Challenger the extra kick of speed it needs to reach space. Once ignited, there is no way to turn them off.
In engineering terms, it's 6 million pounds of thrust. By the time the shuttle got up to 5,000 feet, it's already going faster than the speed of sound. So that's a lot of power.
The rocket boosters are shipped from Morton Thiokol's base in Utah to Kennedy Space Center. NASA engineers then assemble the 7 sections into a complete booster rocket. Two strips of synthetic rubber called O-rings sit between the middle segments. Each one is just a 1/4 inch thick. They are designed to seal in superheated exhaust gas. The first O-ring is expected to do the job. The second is a safety backup. The O-rings are supposed to be flexible. On launch, they should squeeze and stretch to create a seal. These seals may be small, but they are vital.
A small component can be just as critical and have an effect, a big effect on the performance of a shuttle as a large structural component. And that's the case with the O-rings.
The final chapter in Challenger's story begins when an engineer at Morton Thiokol discovers a problem with the O-ring seals. Roger Beaujolais was inspecting the reusable rocket boosters following an earlier mission, that of Space Shuttle Discovery in January 1985.
I went around, and on the first booster, I found on one of the joints hot gas, massive amount of hot gas from propulsion had actually compromised the primary O-ring. So I thought, my God, we came within about 8 or 10 seconds of failure.
Beaujolais discovers that hot gas had blasted past the first O-ring and damaged the second backup ring.
I instantly, in my mind, thought, oh, this has to be caused by the cold weather that preceded this launch.
When Discovery launched, air temperatures were just 53 degrees. At the time, it was the coldest launch on record.
O-rings are made of silicone, but when temperature changes, silicone and rubber behave a lot alike. Now here's a piece of rubber. Room temperature, very flexible, very elastic. It's much more responsive in returning to its original shape when you bend it. But what happens when rubber is kept at low temperatures, chilled like those O-rings were? We put some rubber in dry ice for a couple hours, and the rubber is much less elastic. It doesn't bounce back into place quite as quickly as at room temperature. And this is what happened to those O-rings. In the chill of that January morning, they were no longer able to create the seal between those two sections of solid rocket booster.
NASA has rated the O-rings mission critical. If the freezing temperatures cause them to fail, superheated rocket exhaust could blow out between the booster's segments. If that happens, it could spell disaster for Challenger. On the evening of January 27, 1986, Space Shuttle Challenger sits on the launch pad at Kennedy Space Center. Launch is slated for 9:38 the next morning. A high-pressure weather system has brought freak cold conditions to Florida. The weather is a major concern to Roger Beaujolais and the engineers at Morton Thiokol, the contractor responsible for building the shuttle's solid rocket boosters.
Yes.
They call NASA and tell them it is too dangerous to launch. Beaujolais believes the freezing temperatures will compromise vital seals called O-rings in the solid rocket boosters. But after many delays, NASA wants to get the shuttle into space. The public is watching this particular launch closely. That's because one of the crew is Krista McAuliffe, destined to be the first teacher in space. NASA's reputation is on the line. So when Thiokol engineers suggest delaying the launch yet again, NASA wants to know why.
At low temperatures, the O-rings are not so elastic. And if that happens, neither the primary seal nor the secondary seal will function.
You guys are generating new launch.
After a heated discussion, the decision is made.
At the predicted temperatures, we are out.
Managers at Morton Thiokol advise NASA the launch can go ahead after all. Roger Beaujolais is unconvinced. As night falls, the cold sets in. Temperatures plummet to 18 degrees, incredibly rare for this part of Florida. Ice begins to form on the launch tower.
The ice team was actually amazed at what they saw. There was ice all over the surface structure. Reports of icicles as much as 18 inches long.
It looks like the cold weather will cause a delay after all. In the crew quarters, Challenger's commander, Dick Scobie, calls his wife and tells her there is no chance they will be flying. He believes it's simply too cold. But Scobie is wrong. The following morning, the crew prepare to board Space Shuttle Challenger.
Commander Dick Scobie, Krista McAuliffe, teacher in space. Big smiles today.
The astronauts are unaware of Roger Beaujolais' concern about launching in cold weather. Temperatures at the launch pad are now just 36 degrees, 15 degrees colder than any previous launch. At Morton Thiokol, Beaujolais and his fellow engineers gather to watch. All they can do is hope and pray their fears are unfounded. If the O-rings are going to fail, the engineers expect it to happen just after ignition, when pressures in the rocket boosters are highest.
4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
When it launched, it looked like we were going to have another safe and successful mission all the way to orbit and back.
And we're sitting there, and the vehicle ignites and clears the launch tower, and I turn to Bob and whisper,
Looks like we dodged a bullet.
Beaujolais' relief will be short-lived. He doesn't know it, but the launch is already in trouble. Space Shuttle Challenger is moments away from liftoff. But some of the engineers responsible for the shuttle's solid rocket boosters are worried that the cold weather will cause vital O-ring seals to fail. Yet despite these concerns, their managers have given NASA the go-ahead for launch. 2 seconds into the flight, a black puff of smoke bursts through one of the joints on the solid rocket boosters. The frozen O-rings have already failed. This critical event goes unnoticed, and the launch continues as normal.
Roger, roll, Challenger.
But less than a minute after takeoff, Challenger is in serious trouble.
Now heading down range.
Superheated rocket exhaust begins to escape out the side of the solid rocket boosters and plays over the shuttle's external fuel tank. This tank contains 1.5 million pounds of explosive liquid hydrogen and oxygen. Disaster is inevitable. 64 seconds into the flight, it burns through. Explosive hydrogen gas blowtorches from the external tank. At 73 seconds, the bottom of the tank is blown apart. A fireball erupts in the skies above Florida. Challenger is destroyed by the failure of an O-ring, just a 1/4 inch thick. But But experts are puzzled as to why Challenger didn't explode on the launch pad as soon as the O-rings failed, just as Roger Beaujolais had feared.
One theory is that the gap created by the failure of the O-rings was plugged by particles of aluminum oxide, which is a byproduct of the burning of the fuel in the solid rocket booster.
This plug might have sealed the gap created by the O-ring failure. But 56 seconds after takeoff, something could have dislodged the particles, allowing flaming gases to escape. So what might have caused that? Some experts now believe that the weather may have dealt Challenger a final, fatal blow. Before each shuttle flight, meteorologists use weather balloons to monitor wind conditions in the skies above Kennedy Space Center.
3, 2, 1.
Onboard data recorders gather information on wind shear, the change in wind speed and direction as altitude increases.
We have main engine start. 4, 3.
On January 28, 1986, Challenger encounters the worst wind shear ever experienced by a shuttle during takeoff.
Clears the tower.
Shuttle's rising at about 1,000 feet a second here. The wind speed increased to around 105 miles per hour. And these strong winds and the change in wind speed with height put a considerable amount of strain on the shuttle.
With its external fuel tank and 2 solid rocket boosters attached, the shuttle has a bulky profile, and this is vulnerable to the force of the wind.
So it's thought that this rapid change in wind speed with height, this vertical wind shear that Challenger encountered as it rose, caused those solid rocket boosters to flex. And this dislodged the temporary seal of the O-ring from those aluminum oxide particles.
If it hadn't been for the extreme wind shear, it's possible Challenger might have survived.
The solid rocket boosters are designed to burn for about 2 minutes and get the shuttle to an altitude of around 28 miles, 150,000 feet. If that temporary seal had held for another 60 seconds, it's very likely that there would not have been a disaster.
Next, to see just how long it takes for fuel to turn into a fireball, engineers recreate the conditions that led to the Challenger explosion. In 1986, the Challenger disaster was triggered by freezing temperatures the night before launch. The conditions caused a crucial O-ring seal on the solid rocket boosters to fail, allowing superheated exhaust gas to leak from the right-hand booster rocket. Now, pyrotechnic engineer Dickon Mitchell and his team are trying to discover how long a fuel tank can survive the heat of a flaming gas jet. This white tube represents the solid rocket booster. There's a small gap between 2 sections to mimic the O-ring failure.
We're using the oxyacetylene torch here to simulate the superheated gases that were escaping from the O-ring seal that failed.
On Challenger, the burning gases immediately started to heat the orange external fuel tank.
This can of butane represents the external fuel tank on Challenger. It's going to sit inside this housing, so when it explodes, any shrapnel is contained.
The explosive properties of butane are comparable to those of the hydrogen and oxygen in the shuttle's external tank. For maximum visual impact, Dickon and his team wait until nightfall to trigger the experiment. Flames pass through the gap in the rig and begin to heat the butane tank. After just 2 seconds, the flame melts a hole in the gas tank. The experiment shows just how quickly a fuel tank can turn into a fireball. Once the fuel tank had exploded, Challenger's crew never stood a chance.
Liftoff.
The space shuttle is one of the most advanced machines ever built, developed by America's finest engineers. But the disaster marks a turning point at NASA. There is a gradual realization that the shuttle may not be the solution to America's spaceflight needs.
The Challenger accident and the subsequent investigation proved to not only the people in the space business, but the public in general, that this was a highly complex developmental type of vehicle. And in that respect, it probably meant that we're not going to see the flight rate that we envisioned originally.
4, 3.
Despite its awesome power and technological prowess, Challenger was destroyed by a simple cold snap invading the Sunshine State. It's a reminder that human endeavor will always remain at the mercy of Mother Nature.